Hello. In this video, I'll be walking you through a few practice problems on Fourier series and providing some tips and tricks for how to solve them. We'll be working with the signal already written here, which is modeled after something you might see in a homework assignment. Most questions involving Fourier series will ask you to alter the form of the signal. The way to go about this is almost always using Euler's identity. For this question here, we want this signal to be expressed as a complex exponential rather than as a sinusoid. To do this, we can use two identities. The first of which is cosine theta is equal to 1/2 e to the j theta plus e to the negative j theta. And the second is sine of theta 1/2j e to the j theta minus e to the negative j theta. So our first step is to substitute these identities into our signal. So we've got x of t is equal to the sum from k equals 1 to infinity of 1/3k, and this is where we're going to start substituting in. So for our cosine term, we have 1/2 e to the j, and for our theta, we're going to use everything in the parentheses here, so that's 150 pi k t plus e to the negative j, 150 pi k t. And now we move on to the sine term, which is 1/2j e to the j. Now we'll be using everything within these parentheses, so 50 pi k t minus e to the negative j, 50 pi k t. Now it's just a matter of distributing all of this out. What I'm going to do first is pull out these coefficients and rewrite this as the sum of 1/3k, and then I'm just going to multiply that by 1/4j. And then we just have the multiplication of our two complex exponential terms. So we're going to want to multiply this out, and remember, when we're multiplying exponentials, the exponents are going to add together. So we'll have the same thing out front. So these first two terms, our exponents are going to add to 200 pi k t. Multiplying the first term and that last term, so these two, that's going to be negative e to the j, and then there's a minus sign up here, so that'll be 100 pi k t. These two terms next gives us e that will be negative 100 pi k t, and then these last two terms will give us negative e to the negative j 200 pi. Let me move this. 200 pi k t. And that's all you really have to do. We've distributed everything out. There's nothing we can simplify further, and it's in the form that was requested right here. So a question like this can look a little complicated when you first come across it, but really it's just a matter of knowing your identities and subbing some things in. Alright, this next question is another one that might look a little intimidating, but it's really quite simple when you break it down. It's asking about the signal and whether it displays even or odd symmetry and what that implies about its coefficients. For this question, you'll need to recall that a function has even symmetry if x of negative t is equal to x of t, so this is even, and it displays odd symmetry if x of negative t is equal to negative x of t. Now there's two functions which we pretty famously correlate with each. For even, that's going to be a cosine wave, and for odd, that's going to be a sine wave. So you can imagine that it'll be easier to go about this question with the signal in its sinusoidal form rather than the complex exponential form. So let's rewrite that really quick. It was x of t is equal to the sum from k equals 1 to infinity, 1 over 3k of cosine 150 pi kt sine of 50 pi kt. And basically, all you have to do here is plug in negative t for t and see what happens. So let's go ahead and do that. And nothing's going to change except our t terms within these parentheses. So let me rewrite this to be negative 150 pi kt and negative 50, sorry, my 5s are looking a little bit like 3s, 50 pi kt. So as I mentioned before, we know how each of these terms are going to behave. Cosine is an even function, so we know that cosine of negative 150 pi kt is going to be equal to cosine of positive 150 pi kt, because it has this relationship we stated up here. X of negative t is going to be equal to x of t. Conversely, sine is an odd function, and so sine of negative 50 pi kt is going to be equal to negative sine of positive 50 pi kt. So that's a pretty silly spot to throw that negative, so we'll put it in front of our sum. And you can see that our signal as a whole has the relationship that x of negative t is equal to negative x of t. You can see this whole thing is just negative of this function. So we can make the declaration that the whole signal is odd. What this implies, going back to this form, is that we're not going to be seeing any cosine terms in this form of the signal, because that would display even symmetry. And so if we're not going to be seeing any cosine terms, we can infer that our a of k is going to equal 0, and we know that our b of k is going to have to be non-zero because we can observe odd symmetry. So the major takeaway from this video is that you do not have to do any crazy calculus or math to solve these Fourier series problems. Most of the time, you'll be using trig identities or Euler's identity, and for questions asking you about coefficients, you're going to find that there's some relationship that will make it so either the cosine term or the sine term cannot be present in the signal, and that's how you'll be able to make your inferences about your coefficients. So that's all I have for you today. Thank you for watching. I hope this video helped you out in some way, and I'll see you later.